In this video, we are going to talk about FPGAs and Ethernet, because many people would like to transfer data from FPGA board to somewhere else. And Stacey is going to explain how you can implement this Ethernet in the FPGA. Is that what we are going to talk about?
Yes, that's exactly what we're going to talk about today.
And I would like to point out, we are not going to use like the IP block. You are going to actually build this Ethernet IP.
Yes,
So,
precisely.
and we will do it this way because we would like everyone to understand how it actually works, and maybe if they need to implement something special inside of this network protocol, then they can customize this code, what you are going to actually show today, and people can even download it.
Yes, so it's available for anyone to use.
Okay, so a little bit about what we see here. This is what we are going to create, or this is what we are going to use today in this video.
Yep, that's right. This is the block diagram. So this is a block diagram view in Vivado, and that allows us to easily see the different parts of the FPGA design. So this is the design that's inside the FPGA, and this design is going to be synthesized into a circuit that's going to be implemented on the FPGA. And this particular design will take the switches inputs and the LED outputs, and it will connect them to an Ethernet connection for us to turn the LEDs on and to control and to send data from the switches to Ethernet as well.
So basically, as an example, we are going to do something super simple, LED and switches.
Yes.
But
it could be anything.
It can be anything, yeah.
Yes.
So,
right.
Okay, what do we see in these blocks?
Okay, so, well, in Vivado, the left-hand side are the inputs and the right-hand side are the outputs. So these are physical pins on the device. So the left-hand side has the switches and these are the Ethernet ports, and then a reset and a clock. And on the right-hand side, we see the transmit Ethernet ports and the LEDs, and there's also a UART output and the Ethernet reference clock. And then I have two major blocks here. This block takes the inputs and the outputs, which in our case are the switches and the LEDs, and it turns them into a bus called an AXI stream protocol. And so basically what that does is it takes the data from the switches and the LEDs and it packages it up into a little stream. And that is going to become our Ethernet packet. So you can take any AXI stream packet and you can turn it into an Ethernet data packet. And so this takes our LEDs and our switches and it packages it up. And this AXI bus connects to the Ethernet block, which is going to take those little packets and it's going to turn it into an Ethernet packet and send it on the Ethernet interface. And that's what these two main blocks are here. Okay. This one handles the switches and this one handles the Ethernet.
Okay. So now I think we should mention what kind of board we are going to use in case people would like to try this example, and where they can download this code.
Yes. So this code, the IP repository, which is the code that is used to make up these blocks, is on GitHub and it's available for anyone to use. And this is this here. And so it's this folder here. So if you want to download the repository code, we just can go to the code download section here, and you can either clone the repository or you can download the zip file. And today I'm going to be using this Nexus A7 board, which is the board that you see here. And this is the board that I'm going to be using for this particular example. But any Xilinx board or any AMD board can be used with Vivado as long as it's Series 7 and above, which is all the new ones. And most of these boards can be adapted. This example can be adapted for most of these boards.
Okay, so it's basically any board with Ethernet, or the FPGA needs to be a little bit more advanced, not the most basic one?
Pretty much any board with Ethernet, as long as it's a Xilinx board, because that's what Vivado uses. And this design is not particularly big. So you probably could use quite a small board to use the example.
Okay, perfect. And then as you explain, so basically what we will be doing, we can see there are some switches, there are some LEDs. You can show it also on the camera. So there are the
Yes.
switches and
So
LEDs.
the switches are here. And then we also have the LEDs that are next to the switches here. And those are the switches and LEDs that we're going to be using. And then I also have the power, which is just a USB, one of the mini USBs, I think. And this is the power, and it also is the UART connection. And then all the way over here is the Ethernet port. And that's going to be the Ethernet connection that we're going to be using today. And that Ethernet connection is not directly connected to my computer. It's connected to the network that my computer is also connected to. So this does produce UDP ports packets. It produces UDP packets that can be used on a network. So the FPGA will have its own IP address, and it will be able to talk to my computer on the network. So we will be producing UDP packets today.
So basically this board is connected to a switch, Ethernet switch.
Yes, that's right.
Okay, and on your computer you have small Python application which we will
Yes.
use to talk to the FPGA board.
Yes. And I can show you the code for that as well.
Okay,
Yes.
okay, so now let's start the project. So we know all the background. We downloaded the code from your GitHub. What is the next step?
Okay. So the next step, let me just find Vivado, is okay. So here is Vivado, and I am using version 2023.2.2, but any recent version should be okay. It doesn't really change that much from one version to the next. I am going to click Create Project, and this is going to give me a little wizard to help me create my first project. We're going to just click Next, and I'm just going to give it a name. So it's ETH GPIO example. And that's just the name I'm giving this. And then we're not going to be specifying any sources at this time. So because we are creating a block diagram project, all of our all of the blocks are going to be in the block diagram. You can also have code, but in this case, we're not going to. I will show you where we add the code from the repository. We do it in a different place.
Don't you need to change the path to your project? I'm just asking because go back. Yeah,
this one. No,
yeah.
That's okay.
That's okay.
Yeah,
okay.
That's fine. My home directory is okay. And then we are not specifying sources. And then this is where we choose what part we're using. If you have the board files installed for your board, then it is better to choose the board because then Vivado knows what physical pins on the FPGA map to what ports.
Oh, this was my question because in our block diagram, we could see the inputs and outputs.
Yes.
But there must be some kind of way how you specify which pin exactly is on the FPGA. So if you select the board here, you don't have to do this specification.
You still have to do this, and I will show you how. But Vivado has an awareness of that. It also knows. But we have to also specify our own constraints, and the constraints are what we use to tell the Vivado that those switches or those LEDs are certain pins on the board. And I will show you how we do that.
Okay.
So I'm just going to go down to the Nexus A700T, which is the board that I have. And then that's it. So this is our board. Now it's creating our project. So it's a pretty short setup.
Simple.
Yeah, it is simple. It is simple. So Vivado, it's quite a complicated piece of software, but fortunately we don't have to know or understand everything that's going on. All the features of Vivado, we don't have to understand everything. So I'm just going to go through the basics. And we're going to start, we start from the top left and we work our way down is the general way that we work. So I'm going to start by creating the block design. So if we click create block design, and I'm just going to click OK. And so this is going to create a block diagram view for us to work with. So now we need to also include the files that we downloaded from GitHub.
Okay.
Because we need to take those IP files. Vivado also has its own IP. So those are blocks that Xilinx has included in Vivado that are utilities and functions that you can use that are its own blocks. We're not going to really be using those today because the Xilinx Ethernet block needs to be paid for. And it's quite big and complicated. And so I wanted to have an example of a smaller Ethernet implementation that anyone could use. So we are going to go to settings. So we are going to tell Vivado that I have my own IP that I wrote, and I'm going to tell it where it is. So I'm going to go to settings. I think this Vivado is already set up, but I'm just going to show you how to set it up. We go to IP. And then we go to repository. Oh, it's not added. So we're just going to add it here. And I'm going to go to my Git folder, which is there. And then I'm going to choose Toolbox. So this is the folder that I downloaded from GitHub. And this IP underscore repo is the folder that we want to choose.
We can show it also on GitHub then, so
yes.
everyone knows.
Yes, so it's this one. It's this IP underscore repo.
Okay.
And inside IP underscore repo, there are 4 blocks. And these, or 4 folders. And these are going to be the 4 blocks.
Oh, these are the blocks what we already seen in the block diagram.
Yes, exactly. So Vivado has discovered, it has identified these 4 blocks as being blocks that it recognizes as IP blocks. So we're going to click OK. And then we're going to click apply. There we go. Okay. So now I can add those blocks into the block diagram. Okay. And so we're going to start with, we can start in various places actually. We can start by adding IP. So they give you a button here. There's the same button there. And you can also get that button by right clicking. And then now this is a list of all of the IP in Vivado. So this could be IP that is Xilinx IP, or it could be other third-party IP, or it now includes my IP that I made. So these are all the blocks that it has available to it. And I'm going to search for MII axis. So this is the block that I wrote. And so it's now going to give me this block. So this is the Ethernet block, and these are our Ethernet ports. So I can right click and click make. So these ports, this one and these 3 are our Ethernet ports that connect to outside the device.
They are connected physically to the connector on the board.
Yes, exactly. So I can just right click and go make external. And it will pull out those ports onto the right-hand side because those are outputs. And then I will do those on the left, make external here as well. There we go. So all of these blocks require a clock. And so we're going to handle the clocking and the resets in a moment.
So I have a question now. So
yes.
Can we somehow check how it is now connected? Because you mentioned there should be the specification of specific pin on the FPGA. And so when you double click on the port, something will happen? I'm just curious.
No, it's not that simple, unfortunately. I can show you how that works now, or we can do it in a little bit. What would you prefer?
Okay, we can do it later when we will be doing it for everything. We can do it for everything at once.
Yes, we can do it for everything at once.
Okay.
Okay. So we are also going to add the GPIO one, which is the AXI GPIO. So these are going to connect to the switches. So I'm going to do the same where I make this external, and that's going to be the LEDs. And then the switches make external, and those are the switches. So now we have most of the pins that are relevant. There are a couple of extra ones as well. And so the way that the data is going to flow is the switches. Say, for example, I push a switch. I turn one of the switches on and off. It's going to go from the switch into this little block here. And this block is going to create an AXI packet on this AXI bus. And then that is going to connect to this slave on the Ethernet one.
Mm-hmm.
And then the Ethernet is going to take that packet and it's going to transmit it out of these ports.
Mm-hmm. And then our application on PC will receive the information that we change the switch.
Yes, and so then that transmission will come to my computer that is on the network and it will receive that data.
Mm-hmm.
And then when we want to tell the FPGA to turn the LEDs on,
Mm-hmm.
then it will receive a packet using these ports.
Mm-hmm.
And it'll go into this module, and this module will take that Ethernet packet and it'll make it into a little AXI stream
Mm-hmm.
packet, which is what this protocol is. And then we connect that AXI stream packet to this module, which is going to take the AXI stream packet and it's going to turn it into a signal for our LEDs.
Mm-hmm. So this axis, it's kind of internal bus for communication between the blocks.
Precisely. It's like an internal bus. Yes. It's a very simple data bus. So we're going to click regenerate layout so that it looks a bit nicer. So we can see this is the Ethernet portion and this is the GPIO portion. And we have connected these together.
Okay, you mentioned we need some clocks and maybe reset or something else.
Yes, so the FPGA needs a clock. So we are going to create a clock. We're going to use one of the Xilinx clock, the Xilinx IPs. We don't need to make our own IP for this. So I'm just going to go clock, clocking wizard. I'm used to it being called the clock generator, but it's the clocking wizard in this. So we need to tell off the board is an oscillator, and that oscillator is going to be the oscillator that the FPGA uses as a clock.
Mm-hmm.
So I need to make this external because
so there is a crystal connected.
Yes. So then that'll be the clocking pin, and we will connect it up in the constraints when we get there. And then this reset is not going to be there, actually. That's not the reset we want. So I'm going to double click on this because I want to tell it what clocks to give me. So the input is 100 megahertz and it is going to give me 2 output clocks. So this is for the Ethernet. The Ethernet cores are running at a 50 megahertz clock. And then I also need to create another 50 megahertz clock that's out of phase by 45 degrees. So the Ethernet hardware that's off the board, that's off the FPGA, uses a clock that is 45 degrees out of phase. And that is just the way that Vigilant has designed these boards to work out the timing for the Ethernet on the traces on the board. So it uses a 45 degree out of phase clock, and then this in phase clock will be the clock that the FPGA uses.
So what external hardware is on the board? It's not.
It's the Ethernet magnetics.
Okay.
It's the Ethernet magnetics.
Or Phi or something, because magnetics.
And the Phi, yeah.
Phi, okay.
Well, yes. So this is the.
Let's have a look on the board. Can you open the board again, board specification, so we can have a look?
Oh yeah, sure. We can go there.
Features.
Features.
Okay, hundreds. Okay, but they don't say how exact. Ethernet
it's
Phi.
the reference
It says see the Ethernet Phi section. Oh.
Okay. So we can click on the support tab and go to reference manual.
Because on the board itself, on the top, I don't see anything between Ethernet and FPGA. That's why I ask.
There it is.
Yeah, it says SMC LAN 8720A. Okay.
Yes. It's There we go. So their recommendation is to generate the external fire clock having a 45-degree phase shift to account for the skew introduced by the core.
Okay, perfect. This is good.
So that's what I'm doing.
I'm very happy we found this. We found this information.
Yeah. So that's what this is. And then I'm also going to, where do I turn off the reset? We don't need the reset.
I think it even said it needs 50 megahertz. The documentation I've seen there 50 megahertz. Where was it?
50 megahertz.
Also
clock.
15. Yeah.
There we go. So that's why we're creating a 50 megahertz clock. Everything is just running at 50 megahertz. So we're going to click OK. And so this clock out 2, we are going to make external. And this clock out 1 is going to go to, and you can see that it will tell me
where you can connect.
It recognizes that it knows that this is a clock, and it knows that these are clock ports. So it won't even let me connect it to the resets. So Vivado is quite nice in that it will make sure that you're connecting something to the same bus as something else. Okay, so now we have the clocks set up, and we can also add a reset. So the reason why we need a reset is to give everything an opportunity to start up correctly. So when the clock is supplied from off the board and the 50 megahertz clock is created from that 100 megahertz clock, that PLL needs to lock. So we have this locked signal that connects to this reset module, and that just makes sure that everything is given time, that the clocks are given time to stabilize before everything comes out of reset. So we also just connect the clock up, the slowest synced clock, and then this is our external reset in. So this is if we had to push a button to reset the board. So there is a reset button on this board. And so then we can push the reset button, and that will also be integrated into this circuit to reset everything. And so then we're going to just use peripheral reset and connect up peripheral reset to all these other resets.
Okay.
Like that. And we can regenerate layout. There we go. And that is pretty much everything that is part of the Ethernet GPIO part of the block diagram.
And I think you had also something, the UART for debugging or something.
Yes. So this is the GPIO connecting to the Ethernet. What I also wrote is I wrote a little debug module. So if we go add IP snoop debug. So what this does, this is a really useful module. What it does is it allows you to look at the packets on the bus without interfering. So you'll see this has like a little magnifying glass. So you can go and you can just connect it to any bus and it will tap the packets. It'll duplicate the packets off the bus and tap off at them so that you can get a copy of those packets and you can look at them for debugging. So that's why it's called the Snoop debug. And so I can do it on both. So I can do it on both my one Axie stream interface and my other. And you can actually, if you double click on this, you can make as many interfaces, well, up to 4. You can see these 2 are disabled. So if I put 4 there, then it would allow me to do.
Yeah, you need to press OK maybe or something. Then
yeah. And then this it takes those packets and it puts them on its own Axie stream bus. It's just connect up the clock and the reset. And then we have a UART. Add IP. UART. So Xilinx also has its own UART. But this is just a really simple one. A clock. And a reset. And then this is the UARTX. It just has a TX. Make external. So this way, what we're doing is we're diverting copies of those packets from their respective axis stream buses onto the UARTX interface so that we can debug whatever if we
I
want to
understand,
look
because
at what those packets
we really would like to see if there is a problem or something. We really
Yes.
would like to see if the problem is in the GPIO module or
Yes.
if it's in the RMII module.
Yes. So the other thing is you could, I'm not going to do it now, but you could actually, there's also an ILA, which is another debug module where you can use it for debugging axis streams as well. So it also has that little magnifying glass, but this axis interface isn't any of those on here. But that's this is the Xilinx version of this, where you can kind of use the little thing to connect it to any bus that you want.
So did you write also the axis snoop debug?
Pardon?
This
one?
Yeah,
yes, I wrote that as well. I wrote all of these except this one and this one. So these four, this one, this one, this one, and this one. Those four are the four that are in the repository that are available for download. Those four.
Okay. So I guess now you regenerate again everything.
Yeah, I can regenerate everything. There we go.
Okay.
And the other thing is that we can double click here. And so we can tell it what to put on the switches so we can add a little string. So when I change the switches, then I can tell it to add a little prefix string before the switches number. So it's going to add switches change new value. And so when it creates the packet, it's going to create a little string wrapper around the number so that it's not just spewing out a number, it's actually writing, it's explaining.
Yeah, it's kind of string, so it's a real sentence.
Yes, exactly. And then that's what this does. And then the LED's out, you can choose which part of the packet is the LED number. So if you want to put a string and then your LED number, then you can specify where your LED values are.
Okay.
And how many. So it will be 16 bits starting from byte 31. And then so it'll be two bytes of data.
Okay.
And so this way we can choose where our number is in the packet.
Okay.
And that's what that is. And then it says include carriage return line feed at end of line. So that'll just make it so that on the UART, it goes to the next line for the next packet. And then so that was the GPIO. This one is the Ethernet one, and this one has the Ethernet configuration for the Ethernet. So you can put in the FPGA's IP address, the host's IP address, the ports that they're using, and then the MAC addresses.
So why do we need also host IP address? Because I remember, because we would like to accept only the messages from the host IP, not from whole network, but from specific computer.
Yeah, well, also when the FPGA is sending packets out onto the network,
it has to tell where. Okay.
Yes. So if you change the switch, then the FPGA is going to send a packet. It could send a broadcast packet, but if the IP address is specified, then that will route directly through the switch to wherever it needs to go.
Yeah, I understand now.
So that's why it's both directions.
It was silly question.
No, it's okay. No silly questions.
We have to say where we would like to send the packet. Yeah.
So yes, I'm also including the header checksum because that's not really calculated on the FPGA, just to keep things simple. So because in order to calculate the header checksum, you need to have accumulated a significant, like a portion of the packet. You need to buffer the packet. And I think I'm doing the CRC check, but I'm not doing the header checksum calculation because it's only the header data that changes with the checksum. So if you don't change the header data, then there's no need, then the checksum stays the same.
I have a question. Is there a good website which will explain what is inside of the packet, what we are creating?
Um, I usually just use Wikipedia, but you have to find the right page. You have to find
Can
the
we
right
find
Wikipedia
something?
page
Just get an idea
because
what is inside of this packet.
um the thing with Ethernet is that it's like a stack. So uh okay, here we go.
But yeah, you need to move it.
Yeah, I'm going to.
Okay,
I
okay, okay,
was
okay.
there we go. So this is the UDP protocol page, and you
Mm-hmm.
can see here the datagram structure. So
Mm-hmm.
this is the header, and this is the IPv4. So when
Mm-hmm.
UDP runs over IPv4, then this is the header that's used, and this is the packet format.
Mm-hmm.
So it has the IP addresses, the ports, and the length and the checksum.
Mm-hmm.
And then, like I mentioned, Ethernet is a stack. So this is the UDP. So if we wanted to look at the Ethernet stack itself, so then this is running on top of Ethernet, and the Ethernet stack contains uh, the Ethernet the Ethernet header, which includes the MAC addresses. And I'm trying to find that, and I
Mm-hmm.
can't find it. There we go. Okay. So I will use my own personal explanation that I made. So
Oh, this is nice.
I made this for my YouTube channel because I was like, okay, I'll intro it nicely so that, but I made this for my YouTube channel. So I found this definition that I made for my YouTube channel, and this image shows the Ethernet stack of what we're doing. So we have the link layer, which has the frame header and footer, and that is the Ethernet itself.
Mm-hmm.
And that contains the MAC addresses, and everything else is considered data. And then inside that payload is the IPv4 stack, which contains the IP address header and its own checksum, and then the IP address data.
Mm-hmm.
And then there's the UDP stack, which has the UDP header and the UDP data. And then finally, our data is over there. So our data that we're sending is this. So we are creating the frame header and the IP header and the UDP header and the data to create this whole packet.
Okay, now I
And
understand.
and the way that this looks is you can see here's the Ethernet frame with the values. And then this payload is this frame. So everything, this whole thing fits into this payload.
Mm-hmm.
And then this payload, this is the frame, and then this frame has this payload, and then that contains this. And then our data is here.
Mm-hmm.
So when we create the packet, we have to put in all of this and then only the data. But what's nice is that a lot of this is fixed. A lot of these are just fixed values, so you just hard code them in and forget about them.
Oh, that's why
It,
you could hard code the checksum.
yes. So that's why the checksum is hard. There's a couple of checksums. I think the UDP checksum can be 0. There are a couple of checksums that can be 0, but one of them can't. Otherwise, the switch will throw the packet away.
Mm-hmm.
So the switch will do a checksum check on the packet, and the switch will throw the packet away.
Ethernet switch.
So you need to have the header be the checksums work out.
Mm-hmm.
Otherwise, it's quite difficult to debug.
Mm-hmm. Okay, we can go back now. Now it's clear for me.
Okay, does that make sense?
Yeah.
Okay. So I'm going to minimize that as well. So that's what this is. So that's why we have all of this configuration. Because we have
About
to
the
fill
port,
in.
did you just come up with number for the port, or
I think I used 1, 2, 3, 4 in hex. I think this is this. I think this is 1, 2, 3, 4 in hex.
okay.
It's I think that there's a range of ports that Linux says is okay. There's a range of ports that you can use in Linux, and it's not going to complain
Or conflict with
about you
other
using.
applications.
Yes, yes, exactly. So that's why it's says that you can just use any ports. So
Okay.
I mean, not any ports. There's a number above which you must use. I think the lower numbers are all used for specific things, and then the higher numbers you can pick. So
Okay.
that's why I used that. And then the check destination is to ensure that the FPGA will only use packets destined for itself. So the FPGA, the switch is also sometimes the switch will send on broadcast packets or R packets to because the FPGA doesn't respond to R. So the switch will try and send out R packets to the FPGA and not get a response. And so we don't want those R packets being interpreted as packets for the LEDs, where the FPGA takes the bytes from that packet and puts it on the LEDs. So the FPGA will check that the IP address field matches the FPGA's field to make sure that this packet really was destined for the FPGA.
So it's filtering the packets only only for the FPGA. So what are
Yes.
the R packets?
So the switch wants to know what MAC address it is associated with what ports. I think that's how it works. So it wants to know which IP address is associated with which MAC address. So it creates a list of MAC addresses and IP addresses so that it can identify who's on the network. And the FPGA doesn't respond to ARP requests.
Okay, I understand. Okay, we can close this.
And I think that that's it. This is the UART configuration. So it just asks for the clock rate so that it can work out the board. So this is a 50 megahertz clock, and it's running at a board of 115200. And we've been through the Snoop debug that's just got two interfaces. So those are the four main blocks. So I think that's everything. I think that's everything in the block diagram.
Did we have a look inside of the reset block?
I think
nothing special.
It's not really anything special.
Okay.
So it's not really anything special there.
Okay.
But then now we've looked at all of them, I think, because we'd already looked at the clock wizard.
So what is the next step?
So, well, now we need constraints. So now we have to tell the FPGA, tell the tool which of these ports belong to which physical pins. So the way we do that is with constraints. So I am going to add a constraints file. So we can get constraints for this board from the Digilent GitHub. Okay, I'm just going to drag this tab across because it's... Okay, so this is the Digilent GitHub. These are the board files, which are the files that tell Vivado that this board exists. And this Digilent XDC. So these are the constraints for all of the boards that they make available. So I'm going to go to the Nexus A700T. These are the constraint files for this board, and basically it has the package pin, the IO standard, and the port name. So this is how you map the port name to the physical pin.
So this is basically saying that pin J15 of the FPGA is connected physically by track on PCB to switch 0.
Yes, exactly. It also specifies the IO standard, which is the
3.3 volt
on
signal.
the port. LVCMOS, yeah. So these are the constraints that we're going to be using. So I'm going to download them, and then I'm going to put them in my Git repo here under XDC. And let's just fix the name of it. There we go, save. So then we are using the Digilent constraints for this board. And then we go back to Vivado and we click on the plus and we choose add or create constraints, add files. And then we go to the utils XDC folder. And then it's here, this folder, this file that we use. So it's important that the file that the constraints I use are for my board. You don't want to use someone else's constraints because then it's going to be the wrong pins.
Yeah, you could even damage the board, I guess.
Exactly. Yeah, if you make it an output when it's an input, it could be problematic. So now I've added the constraints. So I'm just going to open it. So it is important that these names match the diagram. So for example, you see this says SW here for switches, and this says SW_0. So I need to change either this or this. So I'm going to change this. Since I only have to do it in one place, if I did this, I'd have to change all 16 of them. And we edit it by clicking on it and then changing this here. So we just do that, and then it will rename it. And so I'm going to do the same, and we also need to uncomment. So I'm just going to uncomment the relevant lines here so that we have the constraints all uncommented, so that you only uncomment the parts of the board that you're going to be using. So you don't need to, there we go, like that. And so then we do the same. So those are the switches and the LEDs. So I'm just going to rename the LED as well. So now we have the switches and the LEDs. And then for the Ethernet, let me just see what's, oh, this is the reset button. So this is called CPU reset. And I'm just going to call that, I'm going to call it _N. Because _N. I like to make them capital, so it's reset _N. The _N just means it's active low.
Yeah. Okay.
There we go. So that's the reset. And then the clock is right at the top of the file. So when we create the clock, we also specify the frequency of the clock and the clock period. So, well, the duty cycle. So in this case, it's 50% and it's 100 nanoseconds. So this is not 100, 10 nanoseconds. So this is 100 meg clock, which is why it says. So I'm just going to make that clock like that. And so this specifies that the clock is on pin E3, and this specifies that the clock is 100 megs with a period of 10 nanoseconds and a 50% duty
These are
cycle.
some kind of properties of the clock or something.
Exactly. That's exactly what it is. It's telling the tool the kind of clock that it's dealing with. So I'm just going to change this to clock so that it matches. And then we need to do the Ethernet. So that's the clock and the reset and the switches and LEDs. And the UART TXD out, the RX. So in this case, the UART output is actually the RXD out. So it's RX from the point of not from the FPGA. The FPGA is transmitting. It's from the point of the receiving side. It's the RX. So the naming convention is flipped for some reason, which is a little bit annoying. But I'm just going to call it RXD out.
I understand.
So it's
basically it describes what should be connected there from the other side, from the outside.
Yes. So it's a bit funny because all the other ones are not like that. It's literally just that one.
But this is very good to point out, because otherwise you can spend a lot of time trying to find out why it doesn't work.
Exactly. So these Ethernet TX and RX ones don't have the _zeros here. So we're going to just RXD and TX EN and then Ethernet ref clock. And then does it have the RX error? It does. So I'm just going to rename these to have the _zeros removed. like that. And then the TXEN underscore zeros. And then the clock output, and then that's the last one. So it's just this guy. And then Ethernet ref clock. So this is the reference clock that's got the 45-degree phase difference. There we go. We put that there. So that is everything.
Okay, we
So now that's
connected
all
our
of the
block to physical board.
To physical pins. Yes, that's right. So we can go validate the design just to make sure that Vivado thinks that everything looks okay. So that means that there's nothing connected where it shouldn't and that everything is configured properly. So, and I'm going to save the program, the project, because we haven't done that yet. So let's save. Always a good idea.
It's a very good idea to save it.
Is there any questions?
No,
or
no,
should
no.
I just
It's very clear.
ahead? Okay. So one of the things that we need to know about Vivado is that Vivado doesn't want it likes a hardware description language as the top level. So this is a block diagram. It wants a top level code file. So I'm going to right click on this block diagram is this. That's how it's represented. I'm going to create HDL wrapper. And what that's going to do is it's going to create a wrapper for my block diagram because Vivado wants to use that as part of the build process.
So basically it's going to be one block with everything what we created.
Exactly. So if we open it, you can see there's the block. So there's my block diagram. And then it's just basically everything connected straight out. So this is useful if you want to put your own code around the block diagram. So say you want to use the block diagram, but you also want to do something else, or you want to use your own code in some way, then you can put the block diagram and put your own code around it. So it's useful. And that's that. So I think we should be able to build it. So we just save. And so this is the build process. So we added the constraints and created the block diagram. Simulation's not really set up, but then this is just the build process. Synthesis, implementation, and generate bitstream. So you can just click generate bitstream.
And it will go automatically through all the steps?
And it'll go through the whole process. It'll do synthesis, it'll do implementation, and it'll do bitstream generation all for you in one go.
So can we explain a little bit what is synthesis, what is implementation?
That's okay. It's just complaining about the parts.
Okay.
So sure, we can talk about what is it doing. So the synthesis is taking the code. So, I didn't show you how to look at the code inside the blocks.
We will have a look inside. We will. Yeah, but
not right now though.
Let's finish this example first, so
okay,
everyone
we'll look inside.
believes that it's working.
Okay, so synthesis is taking the code and it is creating a schematic of the code that determines what parts of the code are going to use what parts inside the FPGA, not specific parts. It's just in terms of general, the kinds of blocks are going to be used for my description. So the FPGA, this project is describing what the FPGA is going to do.
So basically, for example, we know in FPGA there are some AND gates, and our code is transferred to AND gate, but it's not. It has not been decided yet which specific AND gate.
Exactly.
In the chip.
So basically, the FPGA is made up of primarily registers, which are like D-type flip-flops, and lookup tables, which are LUTs. And the synthesis process is taking my description and it is compiling together a schematic made up of registers and lookup tables and other parts of the FPGA. And it is saying, okay, I'm going to create this schematic from this description in the code. And that's the first stage. That's the synthesis stage, which is what's running now. And then the implementation is taking those general types, so just the schematic of the LUTs and the registers and the other primitives, what they're called inside the FPGA, and it's allocating them to specific implementations, specific ones. So it's saying, okay, that LUT is going to be this specific LUT. That register is going to be this specific register. And then the implementation. So the implementation is taking the general schematic that just had these LUTs and these registers and allocating which specific resource inside the FPGA is going to be used for which specific part of the schematic.
Yeah, I understand.
And then in the implementation, there's also the place and route, which is the placing is where it's going to go, and the routing is
connecting
how they're
these
going to be
blocks
connected.
together.
Yes. And that's the implementation part. So the synthesis kind of is the first stage where it's just taking the design and making it into like a little schematic. And then the second stage is taking that schematic and putting it in, implementing it into actual resources inside the FPGA.
Into specific hardware.
Yes, into specific hardware.
Mm-hmm. Okay.
And then it generates the bit stream. So we've actually opened the synthesized. So I can open the synthesized design because we've done the synthesis now. So I can open it and I can show you the schematic. And we'll see what it looks like. And then the generate bit stream takes the... So you can see it's not using up much. Oh, this is not implementation. That's why it's empty. So this is the schematic.
Mm-hmm.
So you can see that we have input and output buffers. And then let me just see if I can find a... Because it's going to be a lot of hierarchy. There we go. Okay. There we go. So these are... So FDREs are D-type flip-flops. They're registers. And I'm just trying to see if I can find a LUT somewhere because there's a lot of registers in this. Let's see if I can find a LUT. There's a LUT. Oh, it's done. Okay. So I'm going to cancel that so that it doesn't disturb what I'm... I don't really want to open... There we go. There's a LUT. So the LUT is asynchronous logic, so it doesn't have a clock. And basically what this does is it is a lookup table. And you can actually see the truth table for the specific lookup table.
Oh, so this is like a gate, but you kind of program what feature it's doing?
Yes, exactly. So the synthesis tool will take the hardware description that I wrote, the code, and it will allocate it to registers, which are flip-flops, and LUTs, which are these lookup tables. And then it will actually say, okay, this LUT must have this truth table. And so this is the truth table for this LUT, which is how it behaves. This is
cool.
The inputs, these are the outputs. Yeah, it's cool. And that's how that works. So you can see in this design, so this part of the design, we are looking inside the network, I think. We're looking inside, what module is this? The packet receiver. So this is the RX side of the Ethernet. And so basically this has the Ethernet... There's my Ethernet input there. And then on the outside, on the output of this device, way over here, I've got a lot of registers in this. You can see there's my Axis stream interface. And so all of this is the circuit in between that does all the processing in hardware. It's quite cool, I must say. This is a lot of...
That's exactly what I wanted to say. Like from this simple logic, you actually create something what can execute software. It's like... Wow.
Yeah. It's really cool. It's a lot of fun. So we can open the implemented design. So we've done, the build is done. It's a relatively quick build because it's a small project. So the implemented design allocates those blocks to specific blocks on the FPGA. So we can see here these methodology. We can see here that these are the specific resources that were used.
These are specific cells in silicon.
So that's an FDRE. Yeah. So these are the specific cells inside the FPGA that were used. So this is a LUT. So for example, if we zoom in here, we can see this is a LUT here that was allocated to this very specific spot in the hardware. And then this is a register. And so the majority of the FPGA is made up of LUTs and registers. What's this guy? Oh, okay. So this is a RAM block. So
Memory.
this is just its bigger memory, basically. So this is just, it's a primitive that stores more memory. It's a primitive that stores more than just one bit because the FDREs are flip-flops, so it's one bit of memory
Yeah.
basically. So this is more complex memory that we can use. So this is block RAM. So for example, I think one of the parts of the design, I am buffering I can actually look and see what this one is specifically. So this is the FIFO, this is the
Mm-hmm.
Snoop FIFO.
Mm-hmm.
So when we snoop on the AXI bus, we store the packets in a FIFO because we have two AXI buses that we're snooping, and if they both come in at the same time, we need to store them because there's only one output.
Mm-hmm.
So we mux between the inputs so that we can store if we're busy routing one packet through in on the one side and then the other one also has a packet, then we can store it. So
Mm-hmm.
that's what that specific piece of hardware is doing. So it's pretty cool to be able to see how the resources are allocated. And then we can also see here, these are the pins that are being used. So
Mm-hmm.
this is the Ethernet receive input buffer pin. And this is the RX error.
Mm-hmm.
So the FPGA, the synthesis tool will place resources according to where the pins are. So the reason why all of these are up here is because these are the pins that we're using. So it is another thing to keep in mind is making sure that when you choose pins that you're going to use, if you're designing a board, that you use the pins, you keep all the resources together that you're going to be using together.
Mm-hmm. Okay, so it's
So
finished.
yes, it's finished. So we
How
can
do you
we
know
can
it's finished?
because it says write bitstream complete on the top right
Ah,
hand
okay.
corner. And also if we look at the console here, it also goes through this bitstream process also goes through something called a design rule check, which basically means that it goes through a list to make sure that you meet that it's done everything. For example, making sure that your pins, all your ports all have pins associated with them
Mm-hmm.
so that all of your constraints are right and there's design rules that need to be gone through. So that's that. And so you can get through implementation and it can still fail. So we
And
can
do you
open
need
the
to
hardware
write these
management.
design rules or these rules or
No,
something?
no, it's done by the tool. So you can configure them, I think. I'm not actually sure. It's not really something that I mess with that often. So I can open the hardware manager. So
Okay.
this
I'm
allows me to
curious.
program this design on the FPGA.
I'm curious if it's going to work.
Open target, auto connect. So now this is connecting to my FPGA through this port here.
Mm-hmm.
Program device, program.
I see LEDs are off. Okay.
Okay, so the LEDs went off because it's just been programmed. So I am going to bring over my handy Python test. So if I change the switches, so it's going to change this number here. So these switches,
It works.
it works. Of course it works. What did you think it wasn't going to work?
We will explain what this application a little bit later, but basically this application is running on your PC and
Yes.
FPGA is reading the value of the switches and sending through the networks to your PC, and this script, this small application is reading the
Yes.
value of the
So
switches.
when I change these switches here,
Yeah.
the signal comes in through here, it goes out through this bus, it goes through here, it goes into here, and it goes out of this Ethernet transmit. And then which is out that network interface there. Where is my finger? There, through that interface.
Yeah.
And that goes to my computer. And then my computer has a little Python script. And that Python script receives that network packet and it tells me what the switch value is. Now, what's fun is that I also have Wireshark running. So you can see the raw network packet happen every time I change a switch. It receives packets on the network, and this is the Ethernet packet. So you can see the network stack happening here. We've got the Ethernet stack, and this last part of the stack is the data, and this is this data, and it says switch has changed, just like I put in that the string, new value, and then the hex value. And what this Python code is doing is it's taking this hex 2840 and it's putting it on this display here. And that is how we're seeing. So what I can do is I can click switches to LEDs and did it work? I can't see the LEDs. Oh no, they didn't. LEDs didn't come on. So we'll have to figure out why that didn't happen.
I would like to point out before we continue, so this application, what you just showed, it's kind of network sniffer. So we can actually read the packets which are traveling through network.
Yes, sorry, I didn't explain what Wireshark was. Yes, Wireshark is the network sniffer.
Yeah.
That sniffs the network.
We are going to debug.
The LEDs aren't coming on now. That's making me nervous.
No, don't worry, don't worry. So we can use the UART now to see something, or?
Yes, we can. We can use the UART. So we have the UART. So just like I added this UART sniffer to Snoop, this is this on putty. So this is connecting through here. And when I change the switches, it appears on here as well.
Okay.
And so we can see the switches are appearing there as
well. So this is the communication between the GPIO module and the MII module. That's what we see here. So we should see also the LED.
Yes, the LED. So let me just see why the LEDs aren't working. So I'm just going to see, maybe I should close the Python program.
Okay. And try it again.
And just see if that's the reason. And I'm going to try and open the Python program again and see if it's if I can do that, just so that it's
so now you are going to reprogram the board?
I think I can just reprogram everything. There we go. Let me well, let's try first. See.
Oh,
there we
it
go.
works.
Okay, there we go. So I think it's just because I needed to close the Python program and open the Python program again. So because the Python is what's sending the packets to the board. So I don't think it was an issue with the board. I think it was an issue with the Python program. Maybe the socket was giving errors. In fact, oh yeah, you see, that's it. I just scrolled up on the Python console and it's saying network is down.
Yeah, but I don't see it. I don't see it.
Yeah. So what I can do now is I can set the values. So we can put whatever number we want in here, and it'll set the values on the LEDs to whatever we want. But I can also do switches to LEDs, which is if I put the switches like this, then it'll take the switch value and it will reflect it on the LEDs. And then all the switches that are on will also become LEDs that are on. So then they line up together. So that's that. So there we go.
This is really
that is
cool.
A little demonstration. Oh, and we can also see, so the thing with the UART, we can see, so the thing with the UART is the UART is showing the raw Ethernet packet data.
Oh yeah, so it's showing also some kind of other characters, but yeah, it's okay.
So it's showing the end of the packet as well, which is the CRC and the other parts of the packet as well, which is why we are seeing these weird bits and pieces here, because we're snooping this AXI interface here, and this already has a lot of the packet infrastructure, which is why it's like that.
Okay, so now it works. First, I would like to see the Python script.
Yes, of course you may. I'm going to open it with something that's a bit nicer to, there we go.
But is this Python script also in your repository, the GitHub repository? Where is it?
Sorry, we can open it in the repository. Let me just find the right browser. this one. So we go to utils. Did I add it in Python?
Okay, perfect.
There it is. So this is the Python code that I wrote that makes, where is it? This guy. So it uses something called tkinter, which is like the GUI part. So it like gives you a little GUI with buttons. And let me just start with, so this creates the network socket, which basically gives Python control of my Ethernet, some of my Ethernet interface, right? So it binds a socket to my Ethernet. It allows Python to send and receive network packets. So at the top here, I can specify my MAC address and the FPGA MAC address, and my IP and the FPGA IP, and also the interface, the network interface that's on Linux that I'm going to use, which this is the interface name. And this is the string that it's going to send. So if you look at the UART, LEDs changed is the string that it sends. So that's that. And then this creates the window, which is this guy. This the create window function is here. So this creates the window. It basically sets up all the buttons and everything. And then this sends an LED packet. So I start with a base packet, which is just the basic. This contains all the Ethernet data, all of that Ethernet header that we don't want to worry about. That's all in here. And then it includes in that the parts of that we do want to change are my IP and the FPGA IP. And then also the value that I want to put on the LEDs and the text that I want to send. So this was the send string, which was the LEDs change. So that takes the base packet that has all of the other header config, and it just puts in the important stuff. Oh, I don't know what happened. And then it sends the packet. So this just sends the packet along the socket. And that's what happens when I push this button. When I push this button, it will run this code. And then the switch value, it receives, the 2000 is just the length, the size of the buffer. So it's going to receive a packet that's anything smaller than 2000. And then it checks if it's for me, because in Wireshark or, on the PC, there's lots of packets flying, especially now we're talking over Zoom. So if I open up my Wireshark without the filters on for my FPGA, it's going to be tons of packets. So this has to filter my MAC address and the FPGA MAC address to make sure that we're only zooming in on that traffic that we care about. And then it's going to decode. And so this 42 just gets the number from the switch packet. So the switches have all of the other text, and that just gets the number. Or I think this gets the data, and then the update switches gets the number. So this gets the data, and then this takes the data, and if I want to update the switches value, this label, update this number here is this code. So it gets the switch value, and then it updates this text with the new switch value here.
The code is actually quite short. We are at the end of the code now.
Yeah, 150 lines. So it's not so bad.
Okay, so basically if someone would like to talk to their FPGA through Ethernet, this is exactly the starting point what they can use.
Yeah, that's a starting point for what they can use.
Okay, and now let's have a look inside of the blocks in our FPGA.
Inside here. Okay, so so the way that we look at the code that's going on inside of these is we can right click on one. So let's pick this guy. Edit, and then we click edit an IP packager. So the other, and I'm just going to click OK here. So the other IP blocks, the blocks that are designed by Xilinx, and other third parties, you can't do this. You can't just click and look inside. But because I designed this and I added it manually in the settings as the IP repository, one of the folders, I can actually look inside, and it gives me this packaging form basically. And one of it, so for example, here, this is where I design what those parameters look like. So I can choose, I can put tabs and I can configure it the way that I want to. And then here we have the code. So this is the switches in and the LEDs out and packaging them up into that AXI format. So this is what the code looks like. And these are the parameters that end up on the GUI here. And there are my switches in and my LEDs out. And here are the AXI buses that I was talking about. So the AXI stream bus, it's like a little packet protocol where you can take your switch event and you can packet it up into a little packet that it sends along the interface. And that's what this does. So I've just got a hierarchy here. So I have split it up into this is the LEDs one, and this is the switches one. So it's separated out into two little modules. The switches one does the switches to the AXI, and the LEDs is the AXI to the LEDs. So if we look at the hierarchy here, this is the LED output. And basically what it does is it counts the length of the packet and it pulls out the numbers in the packet. So say, for example, I want the LEDs to contain the numbers that are found at the byte start. So for example, byte start here is 31.
Oh yeah,
so
this is what we set
31.
in the block.
Pardon?
This is what we set in the properties of the block.
This is what we set in the block. So now we said, okay, byte 31 is going to contain the LED numbers. So then I have a counter, and that counter counts its way through the packet. And then when the counter is equal to the byte start, it's -1 because it's offset from 0. Then we are going to flag that data beat as, or that part, that word, as the number that we want. And then it remembers it. So all we do is, if we've got the start, we remember it. So the data enable just means we must remember this. And then it drives it on the output. So this is, it just, the AXI bus is smaller than the LEDs. So the AXI bus is, this is an 8-bit bus, I think. Yes. So this is an 8-bit bus, and there's 16 LEDs here. So I have to remember 2 words, one after the other. So I have to take the first word and the second word and put them together to create the LED value. And that's what this does. So it takes the 2 words and concatenates them together and then drives that.
Okay, this is something that is like outside of my...
I know.
But I hope this helps, again, people who would like to implement their own things.
Yes.
Because this is just about Ethernet stuff. So this is the block which they would like to probably customize and then send the specific data through this AXI bus to the Ethernet block.
Yes, exactly.
Okay, let's have a look inside of the Ethernet block.
You want to see inside the Ethernet one? Okay.
It's going to be even more complicated.
Oh yes, it will. This is simple. This is the. I will make it easy on you though. Oh, okay. Let's just close this. So I'm just gonna click repackage, and then this will say, "Do you want to close?" Yes. Okay. Bye bye. I'm going to click. I'm going to edit this one.
Okay. Now I'm scared.
No, don't be scared. Don't worry. It's very hierarchical. At least it should be. Yeah, it's not so bad. Let's do the packet generator first. So
Okay.
this is okay. So what we have here is we have the Ethernet pins, and then we have our 2 interfaces. These are the same interfaces that we were talking about before. And then we just have it split up between a packet generator and a packet receive. So I'm going to do the packet generator first because it's actually quite easy. So
this is the transmit.
this is the transmit. So inside the transmit, I have this header gen, and all this header gen is this is a structure of all of the header data that we need. So it's literally, if I went to
So this looks easier than the switches and LEDs.
now I've just gone off. Trying to find that one page that I had open.
The Excel file.
Yeah, the Excel file. Do I need to? Do you think it's necessary? Ah, there it is. So this is just this. That's all that is. And it's just in code form. And all I do is I just take these hard-coded values and I package them up inside here. All of this is just, all of these hard-coded values are just being put inside that format. And a lot of them
what
are
I'm
just
thinking
hard-coded.
about is how long it took you to, create this correctly, because you can make so many mistakes here.
Yeah, it's about being thorough. I think that is like the number one thing that I have learned. And I'm sure that this is something that you have as well. Like even though you don't do FPGA design, if you're doing a board design and you have, so many different elements on your board, that you're connecting up, that you have to be thorough. You have to sit and carefully, logically work your way through step by step through the whole process. So it's just I think that's like the number one the number one thing skill that I've learned over the course of my career is just to be really thorough,
It's same for
very
me.
careful.
It's exactly same as you said, because big work is always created from small parts, and you just need to be sure that these small parts are correct, and then
Yes,
it's good.
exactly.
But if
It's
you
just every
if you
little
are
bit you need to get
if
right.
you are not precise, then
Yeah.
you can make so many mistakes.
The other thing about this code is that this is old. I mean, I wrote it back in 2021, and this is code that I have written. I've written this in some form many, many times over the years. And this particular one is my personal IP that I developed and have kind of refined over the years. So it wasn't that I did sit down and write this all in one go at one point, but I've just refined it over the years. It was much more simpler. It didn't use UDP. It was a raw Ethernet packet. And then I've slowly built upon it over time. So it's not really that much prep. This part wasn't that much prep for the video. It was more, this has been around for a long time. So I basically just package up everything into this, and that's this Ethernet header gen. Where is it here? This header gen is basically just that. It just takes these hard-coded things and it creates the header. I'm just trying to think if this has, oh, okay, this is a state machine. So let me find the state machine, because the state machine is going to be the most enlightening part of this. Here we go. So,
I mean, most complicated one.
well, so I like making my state machine simple. So this state machine is pretty simple, and I like to do that because it is readable. And the more readable it is, the better. So in this packet generator, we have a format that we're following. So the state machine starts in idle, and that means it's not generating a packet. I have nothing to do. I'm just sitting around waiting for something to come along. And then once it finds out that, once it gets kicked into action to say, oh, okay, I've got to send a packet. It starts by sending the preamble, which is part of the Ethernet header. And then it sends the start of frame delimiter, which is another part of the Ethernet header. And then it sends the header, and then it sends the data, and then it sends the frame check sequence, and then it's done, and then it waits. And the reason why it waits is because we don't want to send too many packets. There is too fast. There is a specification for the time that you must wait between packets. And so I am enforcing that waiting period by literally making the state machine wait before it goes back into idle. And so that's basically what the state machine does. And it's broken down. It will be in each state for a fixed period of time. So it'll be in the preamble for the length of the preamble. It'll be in the starter frame for that length. It'll be in the header for that length. So it's a very simple state machine design where it basically stays in each state for as long as it needs to, and then it moves on to the next state.
Okay,
And
I think now I should say, like, if someone is really interested to learn more, then
are you like, this is a bit too much code for my liking?
this is it really goes like away from my area. So if someone
That's
is
okay.
interested to learn more, you have a YouTube channel.
I do.
Okay.
Yes. I think I actually have made a YouTube video going through. I don't know if I've gone through the state machine.
We can show your YouTube channel. Can you show it?
Let me see if I can find my YouTube channel. Is it this one? Nope. Now I've got to go through all of my browsers to find my YouTube channel. There we go. It's this one. So
if someone is interested,
here we go.
Yeah.
There it is. A quick and easy Ethernet frame state machine explained from start to finish. So this video is the state machine that I made 2 years ago. And it goes through. So here this is the header generator. I think this is actually an older version of the header generator. But it still works. It's just a refined version of it. But this is exactly an earlier version of the same code. So yes, if anyone wants specific details on this, then I probably will make another video on this. If there are people who are interested in knowing this, understanding the specific code, then I can make a video that goes through everything in more detail. And then I'll go through like all of the modules and everything and explain everything. I suppose that actually works. That'll work really well because it is in GitHub, and so it will be helpful for people to have a reference for that, where they can go through it in GitHub and see me explain it as well.
Okay. So for me, from my side, this is really everything what I wanted to ask.
Okay, I'm sorry, it's too much code.
Sorry?
No, is it just too much? I didn't want to make it be too codey.
No. It was not too codey. I wanted to understand the whole concept, how it works.
Yes.
And I'm pretty sure now if someone is working with FPGAs, they can, based on your work, they can continue it and they can modify their code and use Ethernet in their project. So that's what was the goal of this video, to help people to start using Ethernet with FPGAs. And I believe it will help them a lot, what you just explained, and also the code which you uploaded on GitHub. So thank you very much for this, Stacey.
You're welcome. You're very welcome.
Okay, if someone has any questions, they can leave them in the comments, or maybe they can have a look on your channel. And you have contact, I guess, on your channel, because I think that's how I contacted you.
Yes, I do. The email address is on my channel.
And you forgot to say, I didn't ask. So what do you do?
Oh, well, you mean what do I do
What's
on
your
YouTube,
job?
or what do I do for a living?
What's your job? Yeah.
I guess it's the same. The answer's the same either way. I am a professional FPGA engineer, and I have been developing for FPGAs. Now it's 15 years.
15
when I started
years.
with YouTube, it was 12 years. And now I have been working with FPGAs as a profession for 15 years. And I work in industry for companies. My area of expertise is really kind of twofold. It's signal processing, and then there's also the networking part. So I kind of end up doing both. It's nice to mix things up a bit. So sometimes I'll have signal processing work, sometimes I'll have networking work. It's a lot of fun either way. And I started my YouTube channel back in 2021 or 2022, because I saw how much proprietary code was, how proprietary the whole industry was. The tools are proprietary, the code is proprietary, and I was really frustrated with the lack of resources for people who were just starting out. And I know when I started out, there were really very few resources available back when I started in, the 2009, 2010-ish. And so I wanted to take what I knew and make it available to anyone else who wants to try it out. So that's me, and that's what my YouTube channel is. My YouTube channel is FPGAs for Beginners, and I post videos on there about FPGAs.
So, but basically you are a freelancer. Yes, you can
Yes.
take any
So
kind of jobs if a company,
yes,
yeah, has
yes.
some
So
kind of request for networks or this kind of FPGA implementation, you can help them.
yeah, I'm very busy at the
You're
moment,
very
so I'm
busy.
not really taking on any new clients. A lot of my, like a professional capacity, a lot of my clients are long-term clients. So I've had clients for like a decade, and yes, I'm a freelancer and I work in a freelance capacity for companies doing FPGA development for them and consulting. Sometimes companies will ask me, is an FPGA appropriate for my product? Like, I've heard of FPGAs, but do I need them for this thing? And how much is it going to cost? And is it worth it? And is it even a good idea? And those are the kinds of things that I help companies with as well.
Uh, okay. Okay, so that's everything for today. I would like to thank you very much, Stacey, for all your time which you spent preparing all these materials. And yeah, I learned a lot. So thank
You're
you.
welcome. I'm very glad. I'm very glad that it's been helpful, and hopefully it's been helpful to you to see a bit more inside the FPGA and what it consists of.
Okay, thank you.
Great. Thank you very much.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedDevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.